Okay, we'll try and go a little bit fast because we lost a little bit of time there. This is what you got is what you got. We're at PyData LA. It is Thursday, December 5th, 2019. I'm James Powell. If you like this talk, you can follow me on Twitter at Don't Use This Code. So if you want to follow me on Twitter, go ahead and do that. Many of us here were PyData attendees, and so we're very familiar with and we use every day packages like NumPy, Pandas, and NetworkX. And more specifically, these packages provide a lot of details and a lot of additional algorithms and mechanisms that we may use. But most specifically, what we're probably using within NumPy is the ND array, within Pandas, the data frame, within NetworkX, we're using the digraph. And as an aside, one question we might ask ourselves is, what are these things really? We might call these things abstract data types, or ADTs for short. And when you think about abstract data types in the context of Python, you might think, oh, Python gives us a bunch of built-in data types like the tuple, the list, the dictionary, the set, the frozen set. We can describe these in terms of being abstract data types, like the tuple is some kind of record type, the list is some kind of collection type, the dictionary is a mapping, the set is something akin to a mathematical set. And when we look at the NumPy ND array, the data frame, and the digraph, we might say, oh, the ND array is an n-dimensional array, so it's kind of a vector or a tensor or a matrix. The Pandas data frame is a columnar or panel data type. The NetworkX digraph is something that looks like a tree or a graph. But when we think about ADTs, we're often thinking about these as having very small APIs. For example, if we go back to the built-in types, we might think about a Python set as having certain operations and certain characteristics for those operations, how performant they are, what the big O complexity is for computing these. And so for a Python set, you might think about it in terms of the intersection, the union, the difference, the symmetric difference, a fairly small set of operations. Or for something like the Python dictionary, you may think about it in terms of just a number of small operations, whether an element is contained in that, setting an item, deleting an item, getting an item. But when you look at the ND array, the data frame, or the NetworkX digraph, you can see the surface area of those is much larger than what you might assume for an ADT. In fact, what you might think is you might think of these as being something like a restricted computation domain. And so when we talk about restricted computation domains, we end up seeing a very common pattern when we're writing Python code. Oftentimes, you're writing Python code and you look at some kind of entity, some business object, some class. And I'll make this a little bit less abstract for you. So maybe some business object. That was a joke. And you might have lots of these. And when you have lots of these floating around in your system, you start to see serious performance problems. And these are a consequence of Python objects being too big, not being cache coherent, and having unbounded computational complexity. And you might address each of these in turn. You might say, well, Python objects are too big, and so what I can do is and one of the reasons they're too big is they carry this dict around with them everywhere, and so one of the ways that I can address this is by adding slots, and this shrinks the size of my individual Python objects, so a system that has millions upon millions of Python objects will use less memory, but unfortunately that's just not very interesting. Slots are not interesting, that's all I'll say about them. You might also look at this problem and say, well, cache coherency is a problem when you have lots of Python objects floating around in a system. And the solution to this is you could have a custom allocator, because nothing in the Python spec says how things need to be allocated. So you can add your own little arenas and custom allocate things to make sure they're cache coherent, and you can more or less solve this problem. The much bigger problem is the unbounded computational complexity of a Python object. And this is what necessitates the need for some kind of restricted computational domain. In other words, you might have some Python object that has some add method, and you might create a Python list, and you might think of it like a vector, even though Python lists are not vectors, they're collections. And you might perform some operation like sum on this, and it just works. But if you think about that object, you can add unbounded complexity to the internals of that object. For example, in this particular case, each one of these items has some hidden dependency that won't be visible to the actual container structure or to the sum function. And so when you do something like this, you start to break certain assumptions that your container type is going to have about how these operations will be performed. For example, that they are independent of each other, that you have some equational reasoning that sum or addition should be associative or commutative. And this very simple type breaks all of those assumptions. And so what you might say is the NumPy ND array is a very nice solution for this, because it gives us a solution to the first two problems, that you have contiguous data, they are unboxed data, it's machine types, so you can specialize the operations. You do a sum on an ND array, you're actually doing machine-level processor instructions for computing that sum. And most importantly, because these are machine types, there are no complex interdependencies. The NumPy ND array gives you a computational domain in which you have specific restrictions, where those restrictions are things like, we know the contents of this ND array are just plain integers, not some complex Python object that can have arbitrarily complex behavior on it. And so when you look at the code that uses a Pandas data frame or a NumPy ND array, it often follows a fairly simple pattern. Pattern looks like this. You do some work within pure Python to load some data. You may do some work within pure Python in order to clean that data, and then you put that into the computational domain. You perform a bunch of operations on it within that computational domain. Within that domain, certain assumptions are held. And because those assumptions are held, those operations could be performed optimally. You can use, for example, machine types and machine operations in order to perform operations within the computational domain. You can say there aren't these hidden interdependencies. You can do things like auto-parallelize stuff. And then at the very end, you need to pop it out of that domain. So you do something like a df.plot. Inside that domain, the data is managed, and so the domain can set certain rules about what happens in order for you to cross that boundary to take the raw Python objects and put them into the domain. Once they're inside the domain, they're fully managed by that domain, and so you can do whatever you want to make that most efficient, and you can address every one of those three problems. What this suggests, though, is that for a restricted computational domain, there won't be a natural bound on the surface area of the API. In other words, for an ADT, you'll have a fairly natural bound on the surface area of that API. An ADT will only provide certain methods that correspond to how you think about that data type, like pushing into a stack and popping from a stack, whereas a restricted computational domain will have to have an API that's large enough to handle all the ways you poke that domain to encourage it or to force it to perform some computation. So this API is going to be much larger. And so it turns out that that was not really an aside, because this is a very critical problem when you need to do something that we're going to talk about in a moment. It turns out when you use an NumPy ND array, you might use that NumPy ND array directly like this. Like you just create an array with some numbers in it. Or you use a pandas data frame and you use that data frame directly. Or you use a NetworkX digraph and use that digraph directly. However, it is often the case that these entities need to be situated in some kind of production or business context. In other words, let's say that you're using a NetworkX digraph, but you're not using a NetworkX digraph in order to do abstract academic graph algorithm exercises. You're actually trying to do something like perform point-to-point OSNR computations for a mesh optical network. In that case, you need to have some representation between the underlying data structure and the entities that it's manipulating. And you certainly don't want to do this, where you say, oh, I'm going to figure out what the OSNR between two transceivers and two cities is, and 0 represents Los Angeles and 1 represents San Francisco. You definitely don't want to do this. And you definitely want to do something like, oh, I'll make them strings instead. That's absolutely pointless. Instead, what you'll probably have is some custom object, and that custom object will have some data that won't necessarily be used in the computation, and you'll put those into your digraph. Now, that custom data might include information that's not used in the computation, for example, the coordinates of the transceiver, so you can plot it nicely, but it's not used as part of the OSNR computation. However, there may be computational elements in there. For example, for that transceiver, you might need to take into account the baud rate because you're doing some kind of power sweep, so you're trying to figure out what's the optimal power for this network in order to get the optimal OSNR. Unfortunately, it may turn out that that information itself is mutable. And as an interesting aside, one of the things that we talk about when we talk about Python dictionaries is, well, Python dictionaries have keys, and there's a restriction on those keys. They're unique, and also they have to be hashable. What we might know about NetworkX's digraph is that it's modeled as a dict of dict of dicts. In other words, if you have a digraph that has two edges in it, U to V and V to W, this is what it'll look like inside NetworkX. And you can see the nodes themselves are the keys of this dictionary, which means the nodes have to be hashable. But if it turns out that the nodes themselves are mutable, then how do you compute that hash? And we've seen this problem throughout, whenever you try and put something into a set or a dictionary, how do you actually compute the hash? In this case, the only meaningful thing you can do is compute the hash on the ID. If you look at this and this doesn't shock you, you really need to take a closer look. Computing the hash on the ID of the object, this is something that we're told we should never ever do. Because we know that we can't hash a mutable object, right? We can hash an immutable object like a tuple all day long. But when we try and hash the mutable object, we get this unhashable error, and we might have created a correspondence in our mind that hashability implies immutability, but there is an important qualification there. And that qualification is hashability implies immutability if you need random access. In other words, if you're actually manipulating these nodes in your graph, and you don't need to be able to pull them out of the graph object, out of that computational domain randomly, but instead, you're pulling them out through mechanisms that you employ on the restricted computation domain. For example, the only way that we interact with the nodes here is by doing a g.nodes. Then we can loosen this restriction for immutability for the hashability of these underlying objects, and we can actually hash them off of their ID. And all we have to then do is write some function called findNodeByLabel that will pull a node out of this thing by its label, and it'll just use g.node. So it'll abide by the API provided by the restricted computation domain in order to interact with what's contained inside of it. And so we can actually bend this little restriction that we've been told from the beginning of when we learned Python was a necessary restriction for creating an object that can be put into a set or a dictionary. However, this is actually not an aside, because where do you put that findNodeByLabel function? It may be the case that you want to create your own business object that represents this mesh optical network. And so you might have some code that looks like this. You have a transceiver object, an amplifier, a span, and you create a network with a transceiver that's connected to an amplifier, connected to a span, which is a length of fiber optic cable, connected to another amplifier, connected to another transceiver. And you put this into your own custom network object that itself gives you some API similar to the NetworkX digraph. And so you can see in this example at the very bottom, I do a .add edge, which is a call on network hex digraph API. And you need to put into that network object somewhere this find node by label function or some add span function. So that might add in 2 transceivers and automatically compute what the span looks like and automatically place amplifiers if the span might be too long by itself. And so you need to amend that API. You need to supplement or add additional things to that API. And how do you actually go about doing that? Well, it turns out that we're told there's 2 general ways to extend types in Python or in any language whatsoever: composition and inheritance. And we may be told that we should prefer composition. This is what people tell us all the time. Inheritance has too many hairy corners, prefer composition. So let's look at the compositional approach we're trying to extend a network hex digraph. In the compositional approach, what we'd have is we'd have our own custom class, and inside of that we'd have some attribute, and that attribute would have the network hex digraph. And so every time that we need to provide some functionality provided by that network hex digraph restricted computational domain, we have to explicitly create a function called addEdge that then calls self.g.addEdge. And you can think that this becomes incredibly tedious, especially since, as we saw in that first aside, the API of that restricted computational domain can be quite large. And it turns out that we'll have to, in every case, explicitly pull out of that restricted computational domain the API points where we need to interact with what's going on there. And so, as an aside, there's a very important question we have to ask ourselves, which is, who are we really? For example, let's say that we are the maintainers of a package called Dask. And as maintainers of that package, we want to provide a Dask data frame that has a one-to-one correspondence between the pandas data frame in terms of the APIs. And how would we actually go about making that happen? And if we looked at the source code for Dask itself, we'd see that Dask has a data frame object and inherits from an underscore frame type that they give you. And if you look at that underscore frame, you'll see that it inherits from some other mixin types, but there's no actual view of the pandas data frame in this code at all. In fact, if you look through this code, the only place you'll see it referenced to the pandas data frame is in a decorator called derive from that seems to be mostly used for the purposes of either testing or documentation. And so, in order to maintain that correspondence between the Dask data frame and the pandas data frame, you have to go and make sure that every API call that pandas has on the data frame object has its own corresponding call in the Dask data frame object. And you can think that might be a lot of work, especially considering that the pandas API is neither published nor versioned, which means you have to constantly keep up with API changes in pandas on their data frame, on your Dask data frame, where you don't have any explicit contractual target for we support up to such and such version of the pandas API, because there doesn't exist a published or versioned API for the pandas data frame. Now, on the other hand, it's actually a little bit easier said than done, because for a package as large as pandas, it's got a certain maturity and there's a certain limited amount of churn. People aren't constantly adding methods to the pandas data frame, so you don't really have to play that much catch up. But fundamentally, every time there's a change in pandas, there has to be some game of catch up on the Dask side in order to catch up with that. And the compositional approach, you can see, is going to suffer from this. Now, it turns out that in practice, this is not such a hard problem, at least not for Dask, because the Dask maintainers are basically the pandas maintainers. And so they add something to pandas, and they add something to Dask, and they add it at the same time, and it's not a real problem. In fact, as a direct quote from Matt Rocklin yesterday, Dask considers itself to be tightly integrated with the community. And so that's how they avoid that problem. And if you weren't tightly integrated with the community in that particular fashion, you were working on a project of your own, and you weren't also a pandas maintainer, and you wanted to do something similar, provide a corresponding API in your project that could be interchanged with the pandas data frame, you could solve this problem with infra. You could write your own tooling that says every time a pandas release comes out, check for additional methods, and then give us a warning so we have, create a GitHub issue that somebody goes and implements it on our particular corresponding object. But that's going to be a lot of work. And fundamentally, we're not core devs. Oftentimes, when we're taking a package and we're extending it because we need to add some marginal functionality, but we don't want to have the entire cost of maintaining this as one of the main things we have to do. We have probably more to do than maintain an open source package. We have to solve real business problems. And so any of these approaches is just not sufficient. We will probably labor under the assumption that there exists a community of core devs who manage these projects. And so if we can externalize this problem and make it somebody else's problem, then we can say, good luck, that's your problem, not mine. But it turns out this is also not really an aside, because what it tells us is that the compositional mechanism for extending a type requires a lot of maintenance. You have to constantly be tracking down the thing that you're composing, or the thing you're composing against, and make sure that you're always mocking out or stubbing out every single method that it provides. And so that leads us to maybe looking at the other approach, the inheritance approach. And you can think that if the compositional approach is a pull approach, the inheritance approach is a push approach. In other words, if you have some derived type and it derives from a base type, this code alone gives you immediate access to the entire API that's on that base type. And then you can programmatically surgically go in and implement all of the overloaded methods or overridden methods that you need in order to add the core functionality that you desire. However, it is still the case that if there is no contractual API, it's possible that, on that base type, somebody adds some method that doesn't comport with the things that you've already overridden, and they create a little hole in that type. And so, for example, you've almost all seen this if you try to, for example, subclass a Python dictionary and you don't use collections.mutable mapping. You've probably seen this because if you use dict.update, it doesn't itself use dict.setItem. And so you may have seen those problems when you don't create a contractual API. And so it is necessary that in order for any of this to work, you need to have at least something akin to a contractual API where somebody has written out, this is the API, this is what you have to implement, this is what you override. Because in the absence of that, this is intractable. And so an example of going back to dictionary is for the Python dictionary, instead of inheriting from dictionary, you probably will just inherit from collections.mutable mapping, which provides you that contractual API and makes sure that everything more or less works. What that suggests is the inheritance approach will require some maintenance, and some of this maintenance and the need for this contractual API is unavoidable, but there are some minor problems with the inheritance approach. First, when you use the inheritance approach, you start to infect people's inheritance hierarchies, which can be very problematic for a large code base, especially if that large code base has an existing inheritance hierarchy and that inheritance hierarchy is using some kind of naturalistic modeling. As an aside, do not write your code against some naturalistic hierarchy. I don't have enough time to go into why not, but there's a talk that I gave a couple of years back about the pathetic fallacy. And in literature, the pathetic fallacy is this idea of misattributing anthropomorphic qualities to the inanimate. For example, you're writing your code so it kind of matches how you think about the entities in the real world, as opposed to some limited mathematical domain where you're trying to focus on modeling just the aspects that you need in order to perform a computation. When you do that, you inevitably lead to problems confusing the map and the territory, and the whole inheritance hierarchy, the whole thing falls apart. So just don't do that. That, however, was an actual aside, but if that's interesting to you, maybe go see that talk. Now, to take it back to an example, the example that was used in that talk was somebody was trying to build a financial application, and so they create a naturalistic hierarchy where they say, a bond is a type of a loan, and a loan is a type of fixed income product. And you can think that if you need to then insert into this the underlying NumPy ND array that this entire thing might be based off of, or some PyTables object, or some computational domain where you are actually performing the computations, it may be tricky to figure out where to put it in this inheritance hierarchy. And so the inheritance problem is a minor problem here. There's a more immediate problem, which is inheritance often just simply doesn't work, especially with the types that you're used to using directly as part of your day-to-day work. It is possible, for example, to subclass a NumPy ND array. This is possible, and this actually works. You can subclass the ND array, you can put an object into it, you can perform computation. When you perform those computations, you stay within that type. There's even some guidance. There's a piece of documentation. If you ever try to subclass an ND array, I would very heavily suggest that you read through this entire page very carefully about how to subclass this correctly, because the code that I just showed you here, this code's actually wrong. If you do this, this is the result that you get, which is totally nonsensical. And so even the simple example that you just kind of said, that's interesting, it kind of works, doesn't work. Now, you may have tried this already, and you may have tried this with the Python built-in type, like a float, and the immediate problem that you saw was it just doesn't work. You can't subclass a float in Python and expect it to work, because you can subclass it, you get the object out, and then the moment you perform some computation there, you fall out of that type. And so, for example, I create my own custom float, I put some restrictions on it, or I patch it, or I override certain behaviors in some fashion, and then I perform some operation like add it to 0, and the moment I add it to 0, it decays back into a base float. And this is because these types were not originally written to be subclassed in any meaningful fashion. And it is possible, and if you look at something like the pandas data frame, you'll see this problem very directly in the pandas data frame. If you subclass a pandas data frame and then try a very simple operation, like you try to merge it with itself, you'll immediately decay back to a base data frame and you'll fall out of your type, which is not something that you want, because if you start chaining operations, after that first operation, you've immediately lost all of the ability to hook into this type that you originally inherited from it in order to accomplish. Now, it turns out that you can fix a little bit of this with mechanism or infrastructure. For example, in the case of the float, this is from a talk that I gave many, many years ago called Generators Will Free Your Mind, where I create my own subclass of a floating point number in order to customize how it gets printed as part of the formatting protocol. And you can automatically discover all of the API points where you need to patch it out, and patch it out automatically using a class decorator, or in the original talk using a meta class. And it's possible. It's kind of a pain, but still, I think the fundamental problem exists. This will work, but I think it's still a fairly surprising result when you look at these two approaches and you see they have fundamental limitations where the types were not written to be extended, they were not written to be composed nicely, and they weren't written to be inherited from. And so it's quite surprising to me that the types in Python are just not designed for integration. And most of the data science types you deal with are not like the ND array where it'll just work, but there's some caveats, you have to read through some documentation. They're more like the pandas data frame where it just simply will not work right off the bat. There's no way for you to easily subclass this based off of how they are written today. Now, it may be the case that you go into pandas and you could add a bunch of pull requests and you can make it so that a pandas data frame could be subclassed. And you might get a little bit of resistance because how often do people really want to do this? I don't know, a bunch of you might just be happy to deal with pandas data frames, but you can think in a production context that might be insufficient. But how many people are really using these in a large production context is another question you could ask. But fundamentally, the types as they are written today are not designed for this kind of integration. And in fact, most types in the data science ecosystem are not designed for this kind of integration. You may think that there may be one more choice besides composition and inheritance. You might think that there might be an object construction approach by which you could find a way to make this work. And an example of what you might think of when you try and think of this object construction approach is you might think of something that was added in Python 3.7, the data class. And you can think that the data class puts behavior onto a type without inheriting or composing. It programmatically uses a class decorator in order to add behavior to the type once the type has been constructed. And you might think that you might be able to extend this. And so an example of something that I've never seen anybody do, but might be a very interesting area for research is to create your own graph type and then to use decorators in order to create business objects that represent that type, like a mesh optical network that has the behavior of a network X digraph, instead of by inheriting or composing, but by using a class decorator to then construct to add those methods dynamically once the type is constructed, something that looks like this. I wonder how well it would work, because I don't think I've ever seen anybody try this. And so what this leads us to is a very interesting result, that it's surprisingly difficult to situate core types in the data science ecosystem into a business context. I gave a talk a couple years back called Integration with the Vernacular. It talked about a smaller set of this problem. It talked about restricted computation domains, and specifically NumPy, and how NumPy poorly integrated with the Python vernacular. And it goes into some details of where this is actually a real problem. I mean, you need to build something bigger than just manipulations on an ND array. You need to have objects in your system that are not just matrices or vectors, but something that have some additional business meaning associated with them. And you just run into a bunch of brick walls every single time you try it. It turns out we do fundamentally need better mechanisms for integration in the tools that we have. But as an aside, and this is our final aside, and an example, I want to show you something very interesting that results from all of these. And this is truly an aside, but it's actually quite interesting. We all know that in Python, you can write a get adder on a type, and this can hook into what happens when you look up an attribute on that type. And so here, if you ask this type for some attribute that doesn't exist, it'll give you the number 10. And you know that if that attribute already exists, this code no longer works because get adder belongs to a protocol, and so instead of implementing get adder, you need to implement get attribute. But you know that these two hook points where you can hook into what happens when you do type dot or instance dot something. And you know that there are also protocol methods like len that you can implement in order for this type to be able to respond to what its length is. But if you try and use get attribute in order to implement len, this doesn't work. This doesn't work. You can't tell get attribute, oh, when somebody asks me for my len method, give it this particular method. But you also know that there are other protocol methods that are on that same data model page, which talks about how len and repr and hash work, like getState. And getState's used for things like pickling. And as an aside, within an aside, don't use pickle. I wish I could tell you why not to use pickle, but that's the end of that aside. Don't use pickle. Now, what's surprising is this actually does work. And so certain parts of the data model you can patch out using get attribute, and certain parts you can't. Len you can't patch out, but getState for pickle you can patch out, and it works. And the question is, why does that work? Well, if you look into the CPython source code, you can kind of figure out why it is. When you're doing a len, you end up calling this PyObject size in the abstract implementation of the Python objects. And inside of that, you can see on the third line here, you have actually on the fourth line here, you can see it does a m pointer dereference sq length, which actually pulls that function. So it does a direct pointer access rather than going through the get attribute protocol. And this is why you can't dynamically patch out some of these underscore methods. And if you look at how getState works, you might see that for PyObject, there's a getState, and what it does is it actually does an attribute lookup, so it does follow the get attribute, get adder protocol, and so that's why that one works. And so what this should lead you to is a very interesting dichotomy that nobody ever really talks about that exists on all Python objects. That is to say, Python methods are split between methods that have a TP method backing, things that are actually implemented as part of the underlying layout representation of the type, that are direct pointer accesses in the CPython source code, and things that actually go through the attribute protocol. And getState is an example of the latter, and len is an example of the former. And if you're curious about what that protocol looks like, you can go into the include module in CPython object.h. You can see all of these methods and the things that you'd expect. Add, subtract, len, repr, hash, and so on. And you do know that you could patch out an object. You could kind of override all of these methods. You could figure out what all these methods are by looking through the source code, figure out which ones you need to patch out, patch them all out, write a len, a hash, a repr, a getAttr, or a getAttribute, and you can completely mock out an object like this. Now, a question is, why would you want to do this? Well, one interesting reason why you might want to do this is you might want to create a pure proxy. You might want to create some object that proxies another object. In other words, you might have some object A and some object B, and B needs to pretend to be A, either for some debugging purposes or for some logging purpose, or in order to surgically inject behavior into a running system when it's 3 a.m. in the morning and you tell yourself, I never thought I would be here writing code that does this, but I really want to go back to bed, so I'll do something really crazy like this. But you're immediately stopped when you try and do this using any of the mechanisms you know about, because an is-instance check won't work. You can't tell a Python object to pretend to be an instance of another one. You may know that you can, on a meta class of a type, implement instance check. On an instance check, you can do anything. So here is a type that everything is always an instance of. But that doesn't quite work. I mean, it'll work in this case, but there's actually a shortcut. And so that very first line when you ask, is something an instance of another instance? If you're an exact subclass instance, that'll bypass the instance check call. So this will work, but this will fail. Here, this is a type that pretends not to be an instance of anything else, but actual concrete instances of it will no longer obey this instance check protocol. And so there's some little holes in the way that protocol works. Fundamentally, however, because certain types that you might want to proxy out are going to be closed types like int, and you can't implement instance check on the meta class of an int. You have no hook point in which to do that unless you swap out all of the built-in types, which just won't work. Trust me, I've tried this. It's going to be way harder than you think it is, and it won't work. This will just give you a dead end. So unfortunately, you can't proxy even very simple things like instance checks. And heaven forbid, in your code, somebody actually tries something exactly like this, and there's no way for you to proxy that out because you won't be able to proxy the type call. You might think you can, because you might think that, when somebody looks at a type, that's really just a load global operation, and when somebody does a dotted access, that's just a load global and a load adder. When they do a function call, that's usually a load global and a call function. And you might say, a couple years back, somebody added in PEP 523. This was worked on by a couple of colleagues of mine, Dino and Brett, to add frame evaluation APIs to Python, so you can swap out the actual frame evaluator in Python. So I actually had a project that predates that tried something like this called rwatch, where you could read watches similar to what you have in GDB to Python. You could actually say every time Python looks at an object, give a hook point, so you could swap out that object with something else. You'd have some interesting results there. But there were some fundamental cliffs that you fall off when you try this on anything serious. For example, you do this by hooking into the pushing of an object onto the Python stack. And so this will only work for things that actually are evaluated within the Python main evaluator, which isn't everything that might actually be evaluated in a running program, especially one that has some scientific computing use case. For example, if you have some code like this and you Cythonize it, it'll turn into code like this. And if you can squint and you can see on the third line of this code, they do a direct getAttr string, so they don't go through the bytecode, and so they don't go through the VM stack, and so your hook point is no longer there. And you might think this is kind of obscure because I could just say don't use Cython for parts that we need to hook out, but the moment somebody does something like numba.jit and all that code gets swapped out with LLVM IR, you've lost your hook point entirely because you've escaped the Python main evaluator. And so this is going to happen. This is going to happen anytime the objects that you're trying to proxy will go into a C extension module. And think, if you had that C extension module and all you had it was in binary form, and it wasn't even obfuscated, it was just the raw binary, there is no way that you're going to be able to patch that dynamically to figure out all the additional hook points in that. You're not going to be able to trawl that assembly to figure out every time somebody's looking at your object and do something with it. And so unfortunately, even the evaluator mechanism doesn't work. Of all the mechanisms you might think to employ to create a pure proxy, the evaluator mechanism, the bytecode mechanism, the AST mechanism, none of them actually work. They have these weird cliffs where the moment you use numba or Cython, or the data goes into a C extension module, you lose the ability to hook into it. And this is very surprising. There is no way to create a perfect proxy in Python. And it's a surprising result because it turns out in Python, when you have an object, you kind of got what you got. You got that object, and you can kind of mock out certain pieces here and there, but you can't mock out the entire object, which you'd think you would be able to because Python has such a rich runtime. It has the ability to mock out so many different things, to stub out or to implement all of these behaviors. And this is what makes Python so dynamic. But what you might see is that Python is not really fundamentally dynamic. It's more operationally dynamic. In other words, what you can think is that the Python designers created a specific interface for Python. They created hook points at the specific interface, like len and hash and instance check and import hooks and whatnot. And there's just missing parts of that interface, like isInstance or type or the compare is, where you just can't hook into them. And because it was operationally dynamic and there's those missing hook points, you lose this ability to automatically, dynamically extend behavior of an underlying type to, for example, at the far extreme, create a pure proxy. And unfortunately, no amount of interpreter patching can solve this. You might think you could do that. You might think you could use interpreter patching to patch out isInstance, because you could say, well, there's a PyObject isInstance, and it's a symbol I can find, so I can go and I can find that symbol and hook it out. And you can do that, and it'll kind of work. But the problem is that somebody's going to do this. And in the pure proxy case, this should probably work. You should be able to be indistinguishable from the underlying type, but you can't mock out the is check like you can mock out the double equals check. You might think that you can, because you'll go into the C eval and you'll see that there's a compare outcome function that actually does this check, and this is where the exact pointer, this is where the pointer equality is done. The pointer equality check is done. You could say, I could swap this out. Even though it's a static symbol, I can kind of go up the stack to where the evaluator is, use PEP 523 to swap out the evaluator. So when somebody does X is Y, I can hook into what that is. But that won't work, because you'll end up having to try to proxy out something like a NumPy ND array. And if you trawl through the NumPy ND array code, you'll find code that looks like this. This is for assigning arrays, for doing copies. And there's a bunch of code here where they try to eliminate redundant copies by looking into that C type itself. And what you can think is, because the NumPy ND array is fundamentally a restricted computation domain, and the guidance of the restricted computation domain is that inside that domain, the type has full control over the data that it contains, such that it can perform optimally performant computations on that data. It is free to be able to poke at the underlying information of data in whatever fashion it wants, like non-ABI compatible macros or even inline functions. And so there's no way you're going to be able to catch all those points and stub those out. And so unfortunately, it turns out there's really no perfect mechanism for proxying in Python. We do need better mechanisms for proxying. That was really an aside. And so to conclude, to wrap up, I really want you to all ask, what does this all mean? Well, we do need better mechanisms for integration in Python. If we want to situate a data type that happens to be one of the core scientific computing data types that we use, we don't really have easy ways to situate them in a business context by extending them. Composition and inheritance both have serious problems. Nobody's really tried the object construction approach. If we want to take this to an extreme and do something with proxying, there are severe limits on how well we can proxy things, because we have all these weird edges that require in-depth knowledge of how the Python evaluator works or how the Python ecosystem of execution works. And so I want to leave you with one final question, which is, what did this example really have to do with the rest of the talk? What was this talk even about? I don't know. You got what you got. Thank you so much.
Great talk. So if everything has weird cliffs, what is the weird cliff with the descriptor API and integrating that way?
Oh, there's a really major one. Super doesn't work. So everyone says, oh, use super, right? And that's how you call back up into the derived class. Well, I had an example once where I had an API that was mocking out a Windows API for GUI purposes. And so you'd have mechanisms like .font, and it would be a descriptor, it would be a property that you would set, and then behind the scenes it would do some mechanism to match it up to some Windows GUI API. Well, if you need to subclass that in order to, for example, fix a font at a certain thing just to patch out some application because it's 3 a.m. and you just need to patch it out to get it to work so you can go to bed, super properly respects get on the descriptor API, but it does not properly respect set. And so you have to be able to look through the descriptor to understand that you no longer have this ability to be ignorant to whether something is a property or an attribute. You have to actually look through the descriptor to figure out, oh, is this a property or not? Because super will not give you the behavior that you want. And so there are these weird corner cases. Now, the response from a core developer would be, did you really need to do that in the first place? And yes, if you need to employ the full gamut of Python's dynamic behavior to save yourself a lot of time, because you're just one person doing one task and you have more things to do than to track down all of these little corner cases, yes, you do. But the other answer would be, well, I don't know, just hire an intern or something.
So is the answer to use a different programming language?
No, because I think the answer is maybe the answer is this. If you're an analyst and you're just using like pandas data frames and NumPy ND arrays directly, you're using these core types directly, you're happy as can be. You don't really need anything fancier than a data frame. And you may be happy to manipulate that data frame directly. But if you're a data engineer and you need to situate that into a business process, then maybe, and if that's something that happens to be done more and more commonly, as I suspect it is, then maybe we need to go back to some of these core types and think about their extensibility and figure out better ways to extend that. Actually, the answer is switch back to Python 2. Just abandon Python 3. That's the answer. That's the official answer, YouTube. Switch back to Python 2. Python 3 is done for. How about that? Actually, surprisingly enough, some of this stuff works very differently in Python 2 with old-style classes. For example, old-style classes, they dispatch off of the data model method on the instance, not on the type. And so some of this stuff, some of this dynamic patching might actually work a little bit better there, if I remember correctly. And so let's bring Python 2 back. How about that? Any other questions? OK, thank you so much.